Make sure you're aware. We got the practice problems for the quiz, right? Everybody aware of that? Right, so you should be opening that. You should be working through those practice questions. To give you an idea, the quiz is when? Next Wednesday. I don't have rules on is it the full time or not. I think it's supposed to be the full lecture time. Is that normal? Yeah. Okay. So I think that'll be the case. Again, still waiting for directions on that. We'll see what happens. When do you think the practice problems should be done by? I would argue those practice problems should be done by this Friday. So that if you're struggling with any of them, you now have time to get help through the weekend and through the beginning of next week. So you can schedule that time to be better prepared. If you wait till Monday night to have it done, you've got Tuesday to real quickly figure out what's going on behind it. You're not going to learn any of the content. You're trying to cram it in right before the exam. Might work. Generally speaking, that's a bad idea, a bad strategy. Kind of makes sense? It's not due, so don't panic in that respect, but that's kind of the philosophy that you should be kind of thinking about in that preparation. We'll actually talk about some slides about preparation and things like that. I do want to point out the lecture recordings again. So if you miss class or you're late to class, you can always double back and get the lecture recordings. You guys are in the first two columns, right? And it failed to record that first week, and then we had a holiday, and then we've got our two lectures, and we'll get a new one in here. Make sense? I tried putting topics in, and I have since realized that it makes absolutely no sense to put a topic on what that lecture was about, because there's too many lectures that topic is covering. Sorry. Okay? Kind of, sort of? Cool. Which then takes us to lecture. If you get sick of looking at scrolling, look away. Believe where we ended was here? Is that right? Is that where we ended Monday?
Yeah.
Okay. We kind of glossed over this question. Did you guys want to kind of write out some of those calculations so you know what they look like? Or do you think you got it? What's that? Well, this would be the example. Okay. So take a couple minutes to write down your information for that. Please, my iPad worked today. Good. So far it is. So yeah, take a couple minutes. I'll walk around and check on you if you got questions. Go through and set this up. Okay. So let's kind of walk through that process. First thing I would want to go through and do is I want to identify within the question what I've got, or what I'm trying to solve for, rather. So it says calculate the rate constant. Theoretically, if you were looking at an exam, that's all you have, right? You just have the question. So for me, what I would immediately say is I want, come on, pen. I want my rate constant. Okay, I'm trying to solve for that. Okay, after that, I want to know what's given, because to solve for the rate constant, maybe I'm looking at rate equals K times concentration of species. Maybe I'm looking at a mechanism. Okay, so there's lots of different ways we could solve for K, so I want to know what other information I'm provided to direct me to where I need to go. So that's where I could go through and say I've got activation energy. It's usually E sub A, not E lowercase a, just for the record. It's just hard to do that in a computer system. So E sub A is 56.8 kilojoules per mole. Okay, frequency factor. Okay, for the sake of argument, we're just going to say, what the hell is a frequency factor? Well, it's 1.5 times 10 to the, 11th? Per second. I hate writing per seconds, so I will always write it as a fraction. Okay, and I have 298K. I've got a temperature equals 298K. I would write all that information down, and then what would I do? Two options depending on the circumstances for the class. For this class, since you're allowed a sheet of notes, what am I going to do? I'm going to look at my sheet of notes and see where do I see K, EA, T, and something else. Okay? And hopefully what I'm going to find in that process is that I'm going to find this equation. Okay? And if I walk through the given information, I know, or I don't know K, but as part of the stuff I'm working through. Okay? I know EA, I know T. What is R?
Constant, gas constant.
It's the gas constant. Okay? It's a gas constant with goofy units. Are you going to memorize that? No? Then that better be on your note sheet. On your note sheet it says 8.314 or 8.31 is probably fine. Then what does it say?
Joules
Joules per mole times Kelvin. Okay, again, you could write it out 8.314 joules mole minus 1, K minus 1. My argument is doing those inverse units, you're going to screw it up. Okay, that's just experience. Okay, I screw it up when I see it that way. Okay, so I would write it out as that fraction. So I know EA, I know R, I know T, all of those things are given to me. And K, I know I need to solve for. To solve this expression, I would need to know what A was. Well, I'm given another number. What must A be? That must be that 1.5 thing. That's probably my A. With that information, now what can I go through and do? Effectively just plug and chug. 1.5 times 10 to the 11th. Okay. E, this is the button on the calculator. I push the E button. I need my scientific thing. Equals negative 56.8. And it's going to get real ugly. Per mole. Okay, then it says divided by. So what I'm going to do is cheat. And my R, 8.314. Joules goes below. That 1 is going to become moles times Kelvin. You vaguely familiar with that methodology?
Yeah.
Okay. If you're not, I would recommend you talk to me after class. It's not going to be critical, but okay. And then our temperature is also in the denominator because of that slash. So I'm going to put the temperature in the denominator, 298 Kelvin. What happens through this process? My moles cancel, my kelvins cancel, my joules and kilojoules don't cancel, which means what else do I need to do? I need an extra conversion. I need the kilojoules to be in the denominator so that the kilojoules cancel. I need the joules in the numerator so that those cancel. What's the conversion between joules and kilojoules? Okay. If you're even remotely being like, I think it's 1,000, you've already identified a new piece of information. What's that new information you just identified? Something else you need to write on your sheet. Because if you're even questioning whether it is or not, you don't have it memorized, put it on your note card so that you don't have to have it memorized. Whoops. And it helps if you write it with enough space. 1,000 joules is 1 kilojoule. I can now go through the process of entering this into the calculator. Okay? It's going to be an awful, awful mess to go through and process. Okay, what I would go through and do first is run all of that calculation in red into the calculator so that I now have a number. With that number, I forgot the joules, kilojoules cancel. With that number, I'll now go e to that power, get a new number. With that new number, I'll run the last calculation, which is just the multiplication. Okay, I did not run this calculation. Tuesday ran it. One person gave me a number, nobody cross-verified, so I have no idea if it's actually true. I think they said 16 and change.
Yeah, that's right.
Cool. 16.58. Do we need to worry about sig figs? I would say, God, I hope not, because dealing with the exponent in sig figs is going to be a mess. Okay, personally. What should the units be on this number? Where'd you get the per second from?
Everything canceled on the exponent of E.
In E, first off, when you run E, that number had better be unitless. Okay? Because otherwise you're carrying an E to an exponent or to a unit all the way through your calculation. That's not going to be pleasant. Okay? So that E thing, all of those units canceled. What happened with the 1 point? Where did the per second come from?
From the A value.
From the A value that I forgot to include within the calculation. So our final answer is going to come out to be per seconds. Kind of, sort of? A lot of just calculation within that. My understanding is Alex is throwing tons of calculations at you. Okay, yeah. Okay, there is some gray area there. Okay. Questions about what's up there? Sorry. I didn't mean to push that button yet. Were there questions about what was up there? Or are we good? Okay, we'll take that as good. So, doing all that calculation, so even if we backtrack that little bit to this formula, if we look at those components, we can figure out the rate constant if we knew A, this weird orientation factor, right? If we knew the activation energy and if we knew temperature. Can we measure temperature?
Yes.
Yes. Can we measure the orientation factor? That's how the molecules collide. Can you grab an atom? Okay. And some people are like, well, technology is advanced and now we can't. Where did this develop? This developed hundreds of years ago. No, we can't grab atoms. So being able to quantify that activation, or not the activation yet, the frequency factor or A factor, that orientation kind of contribution, is not going to be an easy thing to just be like, oh, it is, of course, 1.5 times 10 to the 11th per second. Isn't that obvious? That's not going to happen. What about the activation energy? What is the activation energy? It's a good little review question. Where is the activation energy? How do I calculate it? Right? Our reaction coordinate, this is energy. There's a reactant, there's product. Where's the activation energy? Say again?
It's in the middle.
I mean, this is in the middle, down there.
At the peak.
Okay? It's at the peak. No, that's the transition state.
Oh.
It's from the reactants too.
Okay, so now we're really nuancing it, which is probably what you were saying in full disclosure. Okay. I am just being obnoxious, but we want to be extra clear with our language behind this. Okay? It's the difference in energy between our reactant and the transition state. Does the reactant exist? Yes. Does the transition state exist? No. It's the point at which you're transitioning across. We can't freeze the structure to be like, what's the energy of this transition? Because the transition is an active position, which means I can't calculate the activation energy easily. So this little problem that we just worked through, A is not easily measurable, activation energy is not easily measurable. Then why the hell is this equation useful? Okay? Kinda, sorta, it isn't. Okay? What this equation does is because someone really smart came along and said, well, this is really telling me that my rate constant is dictated or controlled by some things that I can't measure and temperature, a thing I can measure. So if I go through and now run a whole bunch of experiments where I determine the rate constant and the temperature at which that rate constant was determined, I can now build a graph of all of that data. That graph, come on, work with me, is that slide. So what we're plotting is the rate constant versus the temperature. Okay? And what should that plot look like? Well, that plot should look like an exponential function because it's an exponential function. That's what the equation is. Okay? Current day technology, that's not that big a deal. We'd be like, oh, that's fine. We just tell a computer to go through and run a whole bunch of different fits to it to see what matches. So a computer would go through and it would change this EA over R value and that A value and just constantly change them and cycle through millions of possible solutions until it plotted the exact thing that matches the data. Right? That's really hard for the human brain to do. Right? Or most human brains. I'm sure some human brains can figure that out. Right? But it does introduce some potential other issues. those people listening at home, I apologize for dropping you. That was probably very loud. Okay? If we go through and run our experiment and we just look at 3 data points, and I look at just those 3 lines, or 3 points, does that look like the equation of a straight line? Yeah. So we might fit this to a plot of a straight line. But it's not a straight line plot. How would I know it's not a straight line plot? I have to get more data points so that I could build out and see that that's not going to fit a straight line. That's going to fit some other mathematical function. Okay? And so what we would try and do is start playing with these systems, our rate constant and our temperature, and instead of plotting rate constant versus temperature, I would plot, how about the rate constant squared versus temperature? Does that make it linear? How about the temperature squared versus the rate constant? Does that make it linear? And so what I end up doing is testing a whole bunch of different things to see if it gets a straight line. We can cheat because we know what the line is or what our equation is supposed to fit. Okay? What we're trying to think about is how could we get this into a straight line? Well, what is a straight line? What's the equation of a straight line? Nobody? Yeah, what's the formula for that? That's y equals mx plus b. Where m is our slope, b is our y-intercept. You're like, I didn't have to know math. I didn't want that. Sorry. Okay? And if we go through and look at the equation that we're given at the bottom, really what we have here is y equals a, I don't know, times some weird variable I don't know, times 1 over t. Okay? Where t is our x. So what we want to do is, how do we mathematically rearrange that bottom equation so that it looks like the top equation? Well, do I see an exponent in the top equation? No. So what do I need to do first step? I need to get rid of the exponent. What's the opposite of an exponent? We've heard it. It's a log. So what do? I take the log of both sides. Natural log of y, natural log of this godforsaken huge thing. Do I know log mathematical systems that allow me to simplify and approximate that? I mean, I do. Do you? I don't know. Hopefully you do. Okay. And hopefully what you would get to is the natural log of a, okay, but the natural plus the natural log of e b over x, right? What's the natural log of e? Times something. Just the something. So that simplifies. What do I now have? There's my y. I want to take the natural log of k. There's my y-intercept. There's my slope. There's the x value. All right? So this whole system, instead of looking at all of these raw numbers, why do I keep dropping stuff? Okay, into this system, is I want to take all of this data, temperature and rate constant, and I don't want to plot it as temperature versus rate constant. I want to plot it as 1 over the temperature, and I want to plot it as the natural log of the rate constant. When I go through and do that, what happens? It's a straight line. That was the whole point, right? Ta-da, there's a straight line. Do you need to know how to do all the derivations? No. What do you need to know? The first equation, k equals a e negative e a r t, and then this thing, which I don't want to say out. Which means what should you do in preparation for the quiz? Put it on the sheet. Right? Now that it's on the sheet, you can manipulate and potentially use it. Does that make sense? I think that's a yes. Okay, cool. So, manipulate it and use it. Talking your... But let's do a little bit of modification to help out with this. Okay, that green equation up there, we have y equals m x plus, we're in black, let's just do with it, b. Why is this valuable to me? If I want to solve for EA, okay, what is EA? Well, negative EA over R is equal to, slow it down, don't give me that yet, M. And what did M represent in the equation of a straight line? The slope of the line. So I can now go back to my equation over here, my fit, and this is y equals mx plus b. So for those people who are starting to shout out that number, that's great. Okay, you just jump a little bit faster than I would have liked, which is okay. You're just smarter than me, that's fine. E over r equals, and now you can give me that number. 7, 5, I think I drew through an 8. So to solve for the activation energy, what do I need to do? Do what with 8.314? It's multiply. You're bringing the r across the other side. Whoops, that's an eraser. Times r times r. EA equals negative 3,775.8 times R. Whoops, times R. Ballparking it, R is roughly 10, right? Yeah? So I would get 370,758. That sounds like a really big number, right? Do I really want to write down a really big number like that? So what might we do instead? We could go to scientific notation. What are the units on this activation energy?
Joules.
Joules. So what could we do? We could convert it to kilojoules. And so what we'd end up with, again, ballpark, because I'm estimating R as 10. We'll deal with that minus sign in a second. Okay, it looks like minus sign 370 kilojoules, 77 kilojoules. Okay, did somebody actually run the calculation? Okay, you actually ran the calculation. We'll use the number that you gave me. Use 360? 13. So you should be getting 313 kilojoules. Okay, and if we look at all the mathematics I've written here, I'm getting an activation energy that is negative 313. Does that make sense as a number? Okay, so let's go back to our plot. Not that plot, we have to get rid of that plot. Okay, because if we're going to look at where activation energy is, reactant, transition state, that value. Can that value be negative? It's the transition state energy minus the reactant energy. Can that value be negative? No. Yeah. The activation energy has to be a positive value. It's always going to be higher than your reactant. Why the heck did I get it to be negative? Because I didn't pay attention to my signs. There's two negatives in this. So when I multiply both sides by r, I actually want to multiply by negative r. The negatives cancel, and now I've got a positive value. Everybody catch that? So we made a mistake. We can rectify that mistake that turns it into a positive. Okay? What we're doing is effectively cross-checking for, is this a reasonable answer? Does it make sense for it to reasonably be negative? No, it doesn't. Dang, I made a mistake. Let's double back through and make sure that that mistake gets rectified in case it manifests in changing the number also. Make sense? Okay, based off of at least one person who talked to me Tuesday about something in Alex, they were like, oh, you had to go through and you had to, hopefully this is going to work. You had to go through and solve like using some fancy software, not Mathematica, Wolfram Alpha. Use Wolfram Alpha because they gave you the data that we showed previously. They gave you this data, and you've got two equations with two unknowns, and that's really hard to go through and solve, so you got to plug all this data into the software to go through and calculate it. Or you take the data in that table and you turn all of these numbers into 1 over, and you turn those into natural logs, and you replot it. When you replot that data, ta-da, it looks like that. Now I'm just pulling data straight off the graph. Okay? So if you've got awesome mathematics skills, great. You can be like, oh yeah, I know this software will do all that work for me. That's great. Okay? And then we can, you're such a boomer, Mike. Are you always going to have that software around? Yeah, probably you will. But, except actually, no, you won't. When will you not have that software around? On the test. So using that methodology to solve the question was the wrong way to do it. That was why you needed to use this to be able to solve it. Okay? And you might be like, but the software didn't give me all the stuff to plot all these things. Yeah, you've got a pencil, you've got a calculator. Okay? You've got Excel. You should use Excel. Run those calculations for you. Generates data, then you answer it. Just because a question looks simple does not mean the process to solve it is simple. Kind of make sense? Hi. Questions? Okay. Reactions tend to slow down over time. Why would they slow down? What's that? Does the energy change over time? Okay. If we're running a chemical reaction at room temperature, okay, it may be exo or endothermic, okay, and that's kind of regardless, but that's now exchanging with the ambient environment, and the ambient environment is significantly larger than our chemical reaction, which means the ambient environment temperature does not change, which means our overall energy does not change. What is changing over the course of time? The number of reactants. And if I have less reactants, what's happening to my concentration? I have less concentration. And if I have less concentration, what happens to the speed of my reaction? It also slows down. Okay? So it does make sense, and what they're referencing is right there at the top. It's less frequent collisions. It's the same things that we talked about way back when we first started talking about our kinetic reactions. So if we're looking at a chemical reaction, we will always see our reactions slow down over time. It's always going to be the case. Okay, kind of makes sense? So let's add to this plot a new piece of information. Because as we're making or running our reactant concentration goes down because we started doing what to the reactant? I didn't remove the molecule from the system. Those atoms are still present, but it's no longer reactant atoms. It's product atoms. What's going to happen to the product concentration over time? It should increase. How? Draw a curve. Does my curve make sense? Okay. I want to know what the curve should look like. This curve right now shows in blue is our reactant concentration. okay, versus time. I want to know what my curve should look like with my product concentration.
It should be like, should mirror it.
Okay. What it will be like is somewhat dependent on our reaction, but it should mirror the other one. Right? I'm going to start forming lots of product right away, and then it's going to slowly slow down. Why would the rate slow down?
There's less reactive.
There's less reactants. But it's really high. The concentration is high. Where's the rate? Where's the rate on this plot? There it is. The rate is the slope of the line. Okay? So later on in the reaction, the slope of that line is less steep because it's not producing as much product. Early on, it's very steep because I'm producing lots of product because I have more collisions. So what we're looking at is changing kind of our viewpoint on how we would plot this data and how we're pulling that information out of it. Does that kind of make sense? Which button I want? I want that button. Okay. Okay, so new question. Same deal, same reaction. Okay. A goes to B or product, however you want to look at it. But now I'm going to change the temperature. What would my concentration of A versus time look like? How does the plot change? Does it change? Should it change?
Yeah.
Okay. Talk to the people at your tables. We've got a very vocal yeah. That's good. So what do we decide?
Steeper.
What's that?
Steeper slope.
Okay, we should get a steeper slope. So the rate increases. Okay. The slope was relevant, so we should expect a steeper slope. Okay. Should it still slow down over time?
Yes.
Why?
It doesn't change the amount of stuff happening.
Sorta. What happens to the amount of reactants over time? They go down. And if it goes down, what happens to the number of collisions? It would also go down. So we would expect it to still kind of curl off. Okay. Why does it slow down? Or sorry, not. Why is it a steeper slope? Sorry, that was the word I wanted.
The reaction is happening faster.
Why does the reaction happen faster? Okay. There's a couple different answers to this. Okay. More motion typically means more collisions. More collisions means the potential for more products. Go ahead.
For the product concentration, would it also be a steeper slope then?
Yep. You're gonna,
They would
because
both-
it's going to mirror that same kind of system.
They would both be.
So cool, more collisions. Why else might your rate go faster? Most people didn't come up with the ideas that you guys came up with at that table, which is why I'm pushing on it.
Can you guys
Why else would the rate go faster?
Higher energy in the system.
There's more energy. Okay, why does that matter? If the particles have more energy, why would that speed up the reaction beyond just collisions? The activation energy is still static. If you have more energy for your particles, you have more particles that can make it over that activation barrier. So that's now changing our focus from this plot to a different plot, which I think shows up in a little bit, but not right away. Okay, that would be, that says fraction, okay, and kinetic energy. Remember we had this looking thing? And what happened when we increased the temperature? Okay, it's squished a little bit. Okay, and if we're increasing the energy of the system, the activation energy doesn't change, but the amount of particles that clear that activation energy do change. Make sense? Cool. So how does the rate of reaction change over time? Right, so what we've got now is a simulation. If you've got a personal device, please open up said personal. Sorry, I just remembered that on Tuesday, when I stepped out to do this and tried to come back into the lecture, the recording just bit the dust. We're going to come back to this. We're done at 9:45, right? Okay, I'm going to try and come back to the simulation at 9:40. So we'll get through some more content. We'll come back to the simulation. You've just walked through a bunch of this already and kind of visualized it on your own. The simulation walks through it and shows you what's happening. Okay, so you actually get to see it instead of playing with it in your brain. Kind of make sense? Okay, so we'll come back to this just to make sure I can still draw on stuff. Okay. To that end, we get kind of a little of a break, right? Because what we're going to talk about is kind of the process of learning. Right? I would kind of make the argument this would be a great slide to talk about day one of the semester, not at this point. Okay? At this point, it can be useful. Right? Learning takes time. So how our brains work, right, when we're trying to make all these connections. Right? You're going to start to make random connections as we go through in lecture. When you go through and now practice, you're starting to connect those different spots. Okay, so you start to make paths and connections in your brain from one content area to another content area. That's ultimately what the homework does. Lecture or even reading is just going to get you these spots. You have to be able to get all those spots of knowledge to somehow connect and work together. Except more than likely, when you go through and practice, what's going to happen instead of making those two red dots connect? You're probably going to connect the red dot to the blue dot. And then you'll go, oh, well, that does a beautiful thing up to this blue dot. And, oh, but then I see that connect over to the orange spot. And then the orange spot goes, oh, now I see how that orange spot connects to the red dot, and now you've connected that. That's a wicked long path of detail to connect all that information. Okay? The more you practice, the more what happens is you start to shorten those linkages. If you consider those kind of linkages within your brain, each of those actions takes time. And we may be looking at fractions of seconds kind of within the brain, but our cognitive ability is now going to expand out to not fractions, but tens of seconds. And if you're in an exam environment, are tens of seconds potentially valuable? Yeah. So we want to shorten those connections as much as possible, and that's where practice comes into play. Practice allows you to say, hey, I didn't need to make that long path connection. I can shorten that gap. So it's kind of pictographically is trying to set this up what this is doing. Right? This takes time to chew on and mull over the content, right? Which means you have to constantly be reviewing the content so that you get that opportunity to chew and mull on that content to bring those connections together. Right? If you're only looking at the content, say, twice a week, right, what you're building is the disparate system on the right. Okay? And you aren't able to bridge those connections so that when you get to a quiz or an exam, you're now trying to make those connections during the exam. You're going to screw it up. Okay? That's just the reality of the situation. So the hope is that you spend some time to really learn the content so that when it comes to the quiz, you're actually all connected already and you're just putting that information down and proving that you know it. Kind of make sense? Okay. Where's my buttons? There's my buttons. Okay, and this is another system kind of trying to demonstrate that. So I would recommend you kind of read through this because it's actually talking about the brain chemistry, which is really, really neat and fascinating. People have done lots and lots of studies behind it. Okay? So the more you understand how you learn and how your brain functions, the better off you can hack it to do what you want faster. Okay? Even then, it still takes time. Okay? And one of the reasons why it takes time is these things are challenging. You're trying to make new connections within your brain between new parts of content. That's not easy to do. Okay? And that is oftentimes very painful. Okay? And what will we reflex to do as humans? Okay? intentionally or not, the brain will be like, that's painful, that's not, or that's less painful, I'm going to do the less painful thing, okay, for the instant. And when it comes to studying, you can avoid the studying process and do the less painful thing all the way through. Then the quiz hits, you don't get control over that. That's going to be a very painful thing. Okay? And you're hoping that you've made enough connections to just kind of float through. You shouldn't be hoping, you should know by the time the quiz rolls around, I know this content, I've made those connections, I'm good with it. Kind of, sort of? Okay? And everyone does this. Okay? This semester, I'm struggling to stay on top of everything that's going on. And the only way I'm able to do it is to stay insanely narrowly focused. I'm real nervous at the end of this week because assignments are starting to come due. Okay? And I think I'm going to have a meltdown over the weekend. Okay? Personally. Okay? But what typically happens when it comes to grading is like, grading is painful. I don't want to go through and say, oh, you deserve 5 points and you deserve 10, and now I'm destroying someone's life by giving them 5 points as opposed to 10. Because that's how it feels like. So what do I do instead? Clean the house. Cleaning the house is very, very painful, but it's less painful than dealing with the emotions of grading. So I'll clean the house. Okay? I'll try to find something to do with the kids. Come on, guys, let's go play with Legos. No, we don't do that. No, you do. You do. Please, you do. Okay? And so I have to build systems that are now trying to keep me constantly on task the whole time, because as soon as I fall off task, I know the whole world's going to fall apart. My world. Okay? Your world should hopefully stay together, because all you got to worry about from me is lecture, and I should be able to put that together. Kind of make sense? So as you're structuring your study process, realize it is going to be painful. Schedule times. Okay? I'm scheduling time 5:30 in the morning to about 6:15, because now everybody wants to get up at 6:15 instead of 6:30. I got 45 minutes every morning where I can crank out some work. Okay? It's now turning into like 5 hours Saturday morning from 5 in the morning to 10 o'clock in the morning, where everybody just leaves me alone and I can crank out some work. Okay? Those are now dedicated work things where I've committed the people around me to leave me alone so I can do that. Okay? You need to be doing something similar when it comes to that study process. Okay? And everybody's different. Maybe you're a rock star with the content. Fantastic. Maybe you don't need 5 hours to do it all. You can get it done in 3. But you won't know that until you start that process. Kind of, sort of? Okay. This is a bunch of different things that you could do to kind of deal with procrastination. So I'll leave you to read that later. The biggest thing that I'll point out is right at the bottom, it's a lifelong practice. What we're trying to do is set you up with skills that you would be able to use in the future, okay? And whatever area you choose, okay? And you can look at your own instructor, the current substitute instructor, to realize that it is a lifelong practice because I'm still screwing it up, okay? And I'm older than you all, okay? So I've been doing it for significantly longer, and I still have problems with it. So it's not an easy process. You're going to make mistakes, build on it, work on it, and always try to progress forwards. Don't beat yourself up too much about it. Don't turn it into a meltdown. I hope doesn't happen. Okay? We then move into kind of the next sequence of slides. The date is way wrong. Active is way wrong. I haven't had time to go through and update the slides. Okay? But we can get into this statement at the bottom. In one sentence, what is this graph showing? Okay. Draw a graph that shows the concentration of products over time. This should be really easy. Why should this be easy? You just did it. Okay, cool. I think the first question's a little bit harder, but we'll see. Talk to people around you real quickly. So, in going through and looking at this, that very first question, I can tell you what immediately jumped to my mind. Said, oh, this shows the rate of the reaction. Does it show the rate of the reaction? No, it's showing the concentration of the reactants with respect to time. If I looked at the derivative of this, I would now have the rate of the reaction. So it's not actually showing me the rate of the reaction explicitly. It requires an interpretation. So what is it actually showing me? how the concentration of my reactants change with respect to time. Why are they changing with respect to time? Why are my reactant concentrations changing? You're forming products. You're running through a chemical reaction. Okay? And if we were to go through and show products changing over time, what would we do? Effectively mirror it. This would now be our product concentration, changing with respect to time. Kind of, sort of? Okay. Which is fun, because then, ta-da, next day. Okay. This, I think, is relevant for you all to be looking at actually today. Okay. We're not going to do it in class. I'm going to tell you that you need to be doing this today at some point. Look at the learning objectives for Unit 1 on Canvas. Okay. Why do we need to look at the learning objectives for Unit 1? Unit 1 ends next Wednesday. So you should be looking at those learning objectives and reading it being like, yep, I know what that means. Yep, I know what that means. What the hell is this? Okay? And anything you're like, I don't know what this is, you need to be figuring out now, not next week. So that you're more prepared and ready to go for the exam. Quiz. Does that make sense? Okay. So, catalyst speeds up reaction by lowering the activation energy. Okay. If I'm looking at a plot of potential energy versus the reaction coordinate, what would I draw for a general reaction? I like R, but everything we've been seeing is shown A. So we'll go A to B. Is everybody okay with that? Mm-hmm. Reactants to products. What do I want to draw in this graph to the right? What should it look like? Did you all just get up? Been up since 5. I'm more awake than you all. Admittedly, I probably went to sleep earlier than you. Guaranteed, actually. I promise that. And I went right to reactants, didn't I?
Yeah.
We'll call that A and call this products. There's our transition state. Being able to understand and manipulate these things become really, really critical, both within this class and, heaven forbid, you have to take OChem. It shows up in OChem 2. Right? Literally OChem 2, not also as in OChem 2, second semester. Okay? That's my general reaction. If I add a catalyst, so we've got my reaction shown here, A goes to B, where do I write the catalyst in that reaction?
A2 transition zone, that little area.
Say again?
A2 transition zone in that area. This is
So you're answering where do I put it in the graph. I don't care where I put it in the graph yet. I want to look at this reaction. How do I know I have a catalyst? Where would that information of where a catalyst is specified in that reaction scheme?
You have products.
Okay? Because if we look at a catalyst, what does it do? It changes the mechanism by reacting with the reactants, and then at some point, what happens? It has to be a product. So a catalyst is a reactant and a product. Okay? And if it's a reactant and a product, would I write it on the reactant side? Say, sure, why not? What's wrong with writing it over there? We'll do cat for catalyst. Okay, and if it's a product, I'd write cat for catalyst over there. If I start with it and end with it, do I really want to write it out like that?
No.
Because theoretically, what could I do? Just like a math expression, I could cancel them out. So where do I write the catalyst? Typically, you'll see the catalyst written over the reaction arrow. Okay? It's usually put in that space because it's not really a reactant. It's not really a product. So the only other space we've got is over the arrow. Okay? How does that show up in my energy diagram? So the catalyst changes the mechanism. So if we look at the energy diagram we've got, What's the order of this mechanism? That's a dangerous question, isn't it? Why do we think it's first order? There's only one transition state, so we're saying this is all happening at one individual step. Okay? And since we only have one reactant, we aren't pushing to second order. What would the catalyst do? Well, it's going to change the mechanism. So instead of just A going boop, products, the catalyst has to react with A to create some kind of intermediate. This intermediate then continues to react to go through and make our products. So we change the mechanism by which this happens. Okay? The exact details of how it is changed is beyond the scope of this class, so don't stress about that. But we know it must be changed. So we have to be seeing something happen in here. Okay? And there's a variety of ways that we can show that. But ultimately, because I have a catalyst, what do we know has to happen? How do I know it speeds up? Because I don't see anything about speed on this.
Slower than the transition from the reactant.
Referencing the transition point is halfway there. It's really good. The activation energy, and the activation energy is between the reactant and the transition point. So the catalyst changes that activation energy, and because the activation energy is now smaller, it speeds up the reaction. So I can interpret some speed out of that, but I have to draw a couple parallels or a couple distant connections within it. Does that make sense? Okay. So our catalyst changes that mechanism. In this case, we're saying it changes the mechanism by making it effectively a second order, because we're saying A reacts with it. As long as the stuff that's happening underneath has a smaller activation energy, we're looking at a catalyst. There's a variety of ways that could potentially happen. Okay? But the catalyst must have a lower activation energy. Make sense? Catalysts are a hugely active area of research. Why? It can make a synthesis faster, cheaper, more efficient. Okay? Ultimately, all fancy ways of saying less dangerous or more money. That's what the catalyst is doing. Okay? So depending on your motives, you can target either one of those. Okay? And depending on whether you're an optimist or pessimist, you can say what the industry is targeting. Okay? But those are kind of your two primary categories. Is it safer or is it making me more money? Okay? Both of those are very strong motivators, and that's why catalysts come into a lot of play, because we're trying to find catalysts to do either of those systems. What system already has a wicked amount of catalysts? You're like, Mike has a bunch of catalysts? No, I'm not pointing at me necessarily, I'm pointing at my body and your body. Biological systems have developed catalysts to do virtually every chemical reaction. There's a catalyst. Right? That's kind of neat. So, new diagram. Here's our fractional molecules. Bless you. More molecules have enough energy to react, increasing the rate. Okay. How does this work? So where's our activation energy on this plot? What's that? Cool, wherever we want to put it. So where do we want to put it? Right there, good job. I completely agree with you. That was a great place to put the activation energy for this reaction. Okay. What is the catalyst ultimately going to go through and do? It's going to change how that reaction has happened such that the activation energy does what? It shifts. It shifts where? To the left. And we would call this EA. Cool, I like C, I accept that. I was going to go EA cat, but EAC makes sense. Okay? And now I have more particles that can go through to make product. Okay? So on this plot, our activation energy is literally moving around because the catalyst changes it. In our other systems, we couldn't change the activation energy. We were just saying, how could we change the amount of particles that made product? Now we're actually changing the activation energy with a catalyst. Make sense?
The activation energy will always move the catalyst will always move the activation energy to the left of the graph.
Okay, so that's an interesting question. Would a catalyst ever change the activation energy by moving it to the right? What was the point of the catalyst? Speed it up. Is that speeding it up? No, slowing it down. So we should always see it shift to the left. Okay? Could you create a thing that slows down a chemical reaction? Yeah, we probably wouldn't call that a catalyst, because the whole point of a catalyst is that it speeds it up. Sending request, what was that? Go back here. Okay, so if we look at this chemical reaction, elephant toothpaste reaction, the overall reaction is hydrogen peroxide turns into water and oxygen gas. Okay? I hate demonstrations because everybody looks at this and goes, oh, look at all that foam. Is hydrogen peroxide foamy? Is water foamy? Is oxygen gas foamy? And some people are like, yeah. Did you see the foam? Okay, well, sometimes I'm spitting, but that doesn't quite count. Okay, there's no foam, so why is there foam? Okay, so, oh, it's the iodine. Right? You worked with iodine before? Or iodide? Dissolved in water is just a yellow liquid. Okay, you say, well, the iodine is causing the foam. So I add iodide and I have foam? No, I need the chemical reaction to happen. And I do the chemical reaction and what's produced? Iodide. Is the iodide foamy? Where the hell did the foam come from? You added soap to it. What is this experiment? A fancy way of making soap bubbles. Stupid. Right? In my perspective, it looks explosive and crazy. Well, where? Because I add soap to hydrogen peroxide, I don't get bubbles. I don't get foam. Why do I get the foam? The oxygen gas bubbles out of the solution, which agitates the foam. That's like you rubbing your hands together. This I can see by sticking my hands under the sink and washing my hands. Ta-da, there's the elephant toothpaste. Okay. Admittedly, washing my hands under the sink looks less dramatic than that, but that's what this is doing. Okay. I need to stop doing soapbox moments. Okay. So hydrogen peroxide turns into water and oxygen gas. If I take hydrogen peroxide and put it out on the counter, and I even add soap to it, do I get foam? No. It is naturally producing oxygen gas, because if you leave hydrogen peroxide out long enough, it's just going to turn into water. Right? So it does decompose naturally on its own. But that process is so slow that I don't get any of the bubbling action. So what do? We add a catalyst. The iodide reacts with the hydrogen peroxide to form water really, really, really quickly, and now produce hypoiodite. Don't stress about that if you don't remember your names. IO minus. The IO minus then reacts with more hydrogen peroxide to produce water again and our oxygen gas, and then we reform the iodide. Okay? And it speeds the reaction up. It speeds it up so much that the oxygen gas bubbles vigorously out of the solution, hitting our soap bubbles, which is now generating our frothy layers, and we get the explosion of bubbles. Hooray. So what was the catalyst? Cool. Iodide. Why was it iodide? Thank you for saying it that way. I very much appreciate it. It was a reactant and a product. Therefore, iodide was the catalyst. Is IO minus a reactant and a product? Right. So for the rest of the class, I may not have heard that. One case, it's a reactant and a product. That's why it's a catalyst. And then you said, well, no, it's not a catalyst anymore because it's a product and a reactant. Ands have an order. Okay? If I say oranges and apples versus apples and oranges, that means two different things? In this case, yeah, I guess. So what I would argue is, no, they don't, but you need to be better with your language. What is the catalyst? It is a reactant first, then a product. What was the hypoiodide? It was a product first, then a reactant. That's what's changing the meaning behind those. The iodide, our I minus, is the catalyst. The IO minus is an intermediate along the way. Kind of make sense?
Yeah.
Cool. How do we write a rate law for this? So everybody should be super excited and energetic because you know how to write it right away. You know how to write it right away because you know it's rate equals K, and then you can get less excited. That's fine. Okay, so we got a bunch of people saying H2O2. H2O2 squared?
First order.
Is everybody okay with that? You shouldn't be.
There's an iodine.
Yeah, because I thought it was used in the reagents.
It is used. But when we determine the rate law, what do we look at? The slow step of the reaction. The only step I care about is that first step 1. Okay? So the rate law for the reaction as shown, or our mechanism as shown, is going to be H2O2 times I minus. The concentration of iodide is going to affect the rate. If we drop iodide out of this system, what now becomes the rate law for the reaction? Well, now we need an explanation for the mechanism for the peroxide decomposition on its own. We don't have that, so we can't look at it. Okay? Kind of, sort of? So this is now our rate law. This is now causing us to go back and review that content. We care about the slow step. It's the reactants in the slow step. Why are they first order? Say again?
They're to the first power.
Why are they to the first power? There's only one molecule. Okay? Could I go through and say, oh, I want to finish this conversation. Second order, delete all that. Would I be allowed to say that? The answer is no. When am I allowed to use the coefficient as the order for my species? There's only two circumstances. You calculate it experimentally or from the mechanism. Showing that overall reaction, I've not specified that that's a mechanistic step. I cannot pull the coefficient down. I can only pull that coefficient down for the other scenario because I know this is a mechanistic step. And I know it was a mechanistic step because this has steps. That's why I can pull that down. What's the order for the overall catalyzed reaction? Second order, it's the sum of both those reactants. Kind of make sense? Okay. With that, you are welcome to pack up, but I am going to flip back to that demonstration thingy. And for the sake of the recording, we'll just kind of play with it a little bit. I'm going to use the simulation by myself, whether or not y'all are in here, and just record it. I would still recommend you go in and play with it so you get a feel for what's going on with it. If we look at our overall reaction, we're demonstrating it with particles. I can then plot my concentration versus time. I hit start, and it now shows the change of my reactant over time. Okay, they're showing it as dark blue as opposed to light blue because the dark blue is the reactant and the light blue is product, which officially is actually shown in the diagram. It's not obvious. Okay, so let's click reset. What happens if I increase the number of particles? Okay, I should see the reaction speed up. So when I click start, does it look like that speed, that slope changed? It'd be nice if they left the previous one on there. They don't. Okay? So the initial particles is our concentration. That makes sense. That's our moles. We love that. Okay? Big deal. Let's go through and take a look at the volume. Did we talk about volume at all with any of these systems? There's like, we absolutely did not. Okay? What do we say the rate law was? What do we say the rate law was? Rate equals K. Bracket, right, to some order. Well, don't stress about the order. What does the bracket mean? What are the units on concentration? Molarity. What are the units of molarity? Moles over what? What is liters a measure of? Son of a. Yeah, we did talk about volume. Volume affects your concentration. Okay? So that when we go back to this demonstration, if we decrease the volume, what did we do to the concentration? You increased it, which means what should happen to the speed of the reaction? It should go real fast again. Neat. Okay? What happens if we increase the volume? It should slow down. Okay? Again, without seeing that the other lines on there, it can be kind of hard to nuance that, but hopefully you can pick that up a little bit. Okay, reset. Let's go back to that volume. Reset. What about temperature? Faster if we increase it. So make it real fast. What happened to our particles? They're moving like crazy. And that was where we could talk through the energetics of it. And you can see wicked fast. What happens if we reset, slow this down? Super slow. Okay? And what's going to happen when it's super slow? Okay, almost no reaction. The particles don't collide as frequently, and when they collide, do they have the energy to clear the activation barrier? No. So what happens to your... We're getting hardly any formation of product, and we're effectively getting a flat line because our concentration of reactant isn't changing at all. Okay? We did just real quickly walk through that, and I kind of talked you through it. Again, I would recommend you play around with those dials, and just, for me, it's min-max, but you could do subtle changes within it just to see what's going on with it. With that, we are done. I think we're in a good spot for the quiz next week.